So this video is for what we call the Doppler effect. And in order to understand what the Doppler effect is, we have to know that light and sound travel as waves. Okay, so we'll use a few examples here. Okay, so say you have a tuning fork and you take a little metal rod and you strike the tuning fork, right? If you've done this before, you notice that the tuning fork starts to vibrate and it starts creating this ringing sound. And if we could take like a microscope, or we could zoom in to see the molecular level, we could see that these air molecules are repeating, going back and forth between condensing and spreading out or expanding. So if we look at a molecular view, you can kind of see there are areas that are highly condensed of air molecules, and then there are areas that are more spread out. So this is a wave. In the same way that these molecules are compressed and then expand, in the same way that a wave might exhibit in a pool. So let's say you are in a pool, okay, and let's say you take a board and you push it one way. And then as soon as you do that, you go ahead and pull it back the other way. Like that orange. Okay, so you are going to create, and you're going to see a waveform. Right, so just as a wave has distance between the two peaks of waves, like this point and this point, that's also true for waves in the air or in the atmosphere, like how we created one with the tuning fork. So just as we create and push, as we push the board, more water is going to be higher than the average height or the normal height of the pool, right? So this is what we call our wavelength. Okay, that's also the same thing as the areas of condensed air molecules. Wavelength. All right, we also have one here. So the distance between compressed air molecules and the distance between waves is going to be measurable. It's something that we can actually see. Also, as we pull the wave, we are taking water away from it. So those are going to be the low points. Just like these are our low points, right? So we could also measure those in terms of wavelength. Also, just as we are striking a tuning fork, it's not like it just moves in this direction, right? As sound exudes from an object, or vibrations exude, it goes in all directions. So no matter where you are, as long as the tuning fork is not moving, as soon as you strike it, that sound is going to go in every direction for you to hear. And it's going to be that ringing sound of the compressed areas versus expanded areas that gives it that sound. So with this idea that the air is compressed and expanded and it goes in every direction, we can take this tuning fork again, we can strike it with the handle, and this time we can look at it in terms of circles. Oh, if it'll let me do it. Let's see. There we go. Not that one. Keep trying. Okay. So these waves are traveling in every direction. Okay. It's exuding from the pitchfork. And if we could somehow take a side view of the waves traveling, we would see, say we somehow turn it around, we would see that it would actually look similar to the waves we just saw, where the peak of the wave, also called the crest, is also where that area of expanded air molecule, or excuse me, compressed air molecules are found. All right, so compressed, and then it's kind of more spread out, and then compresses again, then spread out, and then compressed. Right, so we mentioned the distance between waves is called the wavelength. Okay, but let's also take a look at, maybe we have a different tuning fork. And this is something hopefully you can kind of recall from, or as you do the simulation, the simulation will definitely help with this idea. Maybe we have a smaller tuning fork, and we strike it with something else. It's going to have, and maybe if we look at it, it's going to have smaller circles surrounding it. Kind of like that. Let's do one more. Oh boy. Try there. Okay. So, again, if we look at the wavelengths from the side, not possible really, but just imagining it. All right, so what could we say about these two things? So the distance between wavelengths over here, let's make this one green. This one has a greater wavelength. But also in the simulation, they'll talk about frequency. So frequency is the amount of times a wave travels over time. Basically, how many waves pass through a certain point over a given period of time. So what that means is if you have a greater wavelength, that is going to take a longer time for waves to pass through a given point. So a greater wavelength means lower frequency. Okay, if we look at our second tuning fork, this one has a lower wavelength. Right? Because if we look at this, there's really not a lot of space between them. The wavelength is very small. So a lower wavelength means higher frequency. Right? And you can also see this, you've probably seen videos of this. You have like different wine glasses and you put different amounts of water in them and you hit them on the side. They're going to have different pitches of sound. The frequency determines the sound. Where if you have a higher frequency like this one, you're going to have a higher pitch or higher sound. Something like, ah. Right. If you hit the lower frequency one, that's going to have a deeper sound, kind of a lower sound, like a bass. Ah. So we can figure out the frequencies, or we can kind of estimate their frequencies by just the pitch and determining if it has a higher pitch or lower pitch, we can figure out the frequency of that. So let's kind of create a little experiment here. Let's say we take our tuning fork and we have our sound waves that we are aware of, and let's give the tuning fork like a center like of mass almost, like it's where the sound is going to originate from. So let's just kind of put it in the middle. Okay. So we take it, we strike it, right? And we're going to give it some sound waves. Really bad at making sound waves. All right. There we go. Let's make it a little bit bigger. There we go. And this time, let's say we take that tuning fork and instead of keeping it stationary so that the sound exudes from the same spot, let's push it over to the left. And let's say we just move it over here. The sound wave is also going to travel to the left as well. So now we have a sound wave that looks something like that. Okay, and let's do that same thing. Keep moving it to the left. and we'll keep having sound waves going to the left. And let's do that one more time. Okay, so as we are holding this tuning fork after we struck it, we move it slowly to the left. The sound waves are going to be moving to the left. And you might be having a few questions. Why are the sound waves smaller, or just smaller as you move it from the right to the left? Well, this brings up our important topic that we haven't explicitly talked about yet. And you might be wondering, like, you told me this video was about the Doppler effect, you haven't said it yet. So this is kind of where the Doppler effect comes into play. Okay, so as we move something like a tuning fork from the right to the left, let's say each time we move it, we're moving it 1 meter. Right? Each time we move it, that sound is going to, from when we first struck it here on the right side to the end point here, the sound is becoming, there's less vibrational waves. Think about when you strike a bell. It starts off really strong, bong, but then it starts to fade over time, right? So at this point, the sound isn't traveling as much. Okay, so also think about, so I was a track coach at my last school. Think about if you're at a track meet, you have someone stands here, says, runners ready, on your mark, get set, and he has a gun. Not an actual gun. It's like a sound, it just blows smoke. And he shoots the gun. He's right next to the runners, right? Because if the runners were over here and he blew the gun, say, like 200 meters away, it would take some time for that sound to travel, right? So as the sound comes, the person's waiting for it, and then once it hears it, it's like, oh, okay, time to go. So the person with the gun has to be, or the starting pistol has to be really close to the person, or otherwise there's going to be a time delay, right? Because the waves just take time to get, sound travels. It just takes time to get to certain places. So if we go back to our tuning fork movement, let's take a look at our wavelengths and frequencies. So here, our wavelengths are going to be low, right? Low wavelength, right? They're really close together. So whenever they're close together, it's a low wavelength, but it's a high frequency. All right, think about that high pitch, like that, ah. But let's take a look at the other side. Here, it's the opposite, right? This is a high wavelength, low frequency. All right, so that's our bass. That's our low sound. So if you're on the left of it, or the left side of the tuning fork, it's going to sound, ah. It's going to be high-pitched. If you're on the right of it, it's going to be low pitch. But this is true for a lot of things, not just tuning forks. Say you are driving a car, or you're standing and a car passes you. What sound does it make? I kind of do my best to draw a car. There we go. So say it's driving and it passes. This sound is going to change from before it gets to you to the point it gets to you and then the point it passes you. Right? It's going to be like that meow sound. That's the Doppler effect. Okay? Where sound or frequencies, depending on where you are with the object, is going to change. Because maybe you're standing right here and you hear it in the high sound like that meow. And then as it passes you, it's going to be that low sound. So then it's going to change over time. Right? And that is our Doppler effect.